Welcome, everyone. I would like to introduce Meredith Patterson, and she's going to talk about the LANGSEC 2011-2016. And if you have any questions, just please raise your hand and I'll bring you the microphone. Thank you.
Okay, thank you. This is going to be kind of a weird talk for me because I'm mostly going to be talking about things that other people have done or things that don't exist yet. We'll be talking about the past, the present, and the future of a very young subfield of computer science, which really isn't all that old of a field itself. Although, as we'll see, the underpinnings of language-theoretic security reach directly back to the origins of computer science. Unfortunately, we have a lot of ground to cover in the next 50 minutes, so we're not going to be able to dive incredibly deep into any particular topic. But what I hope to do here is, through what amounts to a bunch of examples that succeed by applying fundamental insights about computability, to give you enough foundation and practical reference material to apply those insights towards improved security and stability in your own work. So what do I mean when I say language-theoretic security? Well, as always happens when you try to attach a name to stuff people are doing, that's kind of a moving target. But roughly speaking, we're looking at about the last 5 years of work between me, Sergey Bratus and his students, FX, Julia Wolf, and a bunch of other people that aren't actually in the security community but just sort of happened along as fellow travelers anyway. But we have to go back to the very beginning, 1936, when Alan Turing was working on the Entscheidungsproblem. This was just a couple of years before he helped a bunch of Polish cryptographers crack the Enigma code and win World War II. So, what do we mean when we say the Entscheidungsproblem? Well, it's otherwise known as the halting problem. So when David Hilbert asked, so is there an algorithm that can find out whether an arbitrary expression in first-order predicate logic is valid, which, as it turns out, is pretty much the same thing as executing a program, Turing took a look into it and found out that no, you actually can't do that. Input into a program in the general case is what drives all of the state transitions in the pieces of a program that handle that input, and as those state changes happen, you just kind of have to trust your execution model that that it knows what it's doing. And as Sergey and Julian Bangert and Bex have demonstrated yesterday and today, we can't always trust that that's going to hold. So either your input handler correctly recognizes the input that it was designed for, or it's going to get manipulated by somebody malicious. However, not all of the news is bad. And for that, we have to move up to 1956 when Noam Chomsky formalizes the Chomsky hierarchy. So we've got a bunch of different, what we call classes of languages. So I mentioned Turing above. And the Turing recognizable languages are those that just map directly onto first-order predicate logic. Below that, however, there are several other classes of languages that you can't express quite as much in. However, they're still very useful for expressing messages. And furthermore, they have properties that actually give us a few security guarantees if we go to the trouble of using them. However, not all parsers can be created equal. Not just are created equal, can be created equal. If you have two different parsers that are interpreting the same data, and they interpret that data slightly differently, there's going to be inconsistency between how the implementations that are attached to those parsers deal with that input. In X509, for instance, we dealt with three major ones: Crypto API, NSS, and OpenSSL. When Sergey and Bex were working on ELF, they noticed, wow, there's more than one parser for ELF in the binary tool chain. What could that possibly be there for? And so there's this thing called the context-free equivalence problem, which unfortunately says that when you have one language and you know the grammar for that language, and you implement that same grammar twice, like say in different languages, for instance, as long as you didn't make any mistakes, And as long as you can, trust all of those fundamental assumptions about the underlying language and so on, you're fine. Those will actually parse this, they will parse the exact same language the exact same way. However, if you have one language and you try to come up with two grammars for it, if that language is any stronger than deterministic context-free, which is, about on par with like JSON, that's not going to happen. And unfortunately, if you are rolling your input handling on the fly, which is to say not generating your input handlers from the definition of that input language, this is the situation that you're putting yourself in. One language, two grammars, and you won't be able to determine equivalence in the vast majority of cases, which means that you can really never prove that those two implementations are interoperable. Okay, so what do we actually know about computability theory and parsing? What can we guarantee on? We know that in the general case, proving the correctness of a program is undecidable. Certainly people do a lot of heuristic things, and they can prove small properties about programs. And there's a lot of work in academia about trying to prove, say, for instance, cryptographic properties of SSL or other interesting security properties of other protocols. But we also know that if you're going to try to pop something, you're going to specially craft a packet or specially craft an input string or somehow specially craft some piece of input that's going to get deep enough into the machine that it can cause problems. And these input languages in the main are not Turing complete. HTTP is not, DNS is not, codecs don't tend to be. There are a few weird exceptions, but they tend to be things like scripting languages, and that's an interpreter anyway. So why would you parse something that was not Turing complete as if it were Turing complete? Sergey and I gave a talk at ShmooCon earlier this year, where we were exploring dozens of old vulns from the past. And we mainly just talked about 3 or 4 of them. You can find that talk online. And my favorite one, I think, was the DNS bug that turned out to have to do with interleaved recognition and processing. Like they would parse part of the DNS packet and then do conditional processing based on what they just parsed, and then process more, and then parse more. You are introducing a Turing-complete system into your recognizer when you do this. If you recognize fully before processing, you can avoid this problem, and you also get some surprising side benefits that we'll talk about pretty soon. So don't mix recognition and processing. The low-hanging fruit is right there. You can get security just by making your input handling do one thing and one thing well, handle the input that it was meant to handle, and throw everything else away. So when did we start taking that low-hanging fruit? That would have been 2005. So there I was in a Red Lobster with a guy that I worked with, and he was telling me about SQL injection. I was in grad school. I didn't know a thing about security. I knew a lot about formal language theory, but that was about it. And so this guy's explaining SQL injection to me, and he's talking about whitelisting, how people use regular expressions to whitelist SQL. And I'm like, well, why would you do a thing like that? I mean, SQL isn't regular. Why would you even do that? Wouldn't you have to use context-free something to whitelist that? And the guy was like, what would that even look like? And I'm like, I don't know. So I went home and started noodling around in Python and figured it out. So, SQL, as it turns out, is deterministic context-free. This is great. If we have 2 implementations that have the same underlying SQL grammar, and conveniently, actual, honest-to-God, real relational SQL engines typically actually do have a parser generator that, that generates their input handling routines for them. No SQL, not exactly so much. But SQL is deterministic context-free. And I know that I only want to accept queries to this database that come from the app that I wrote. And I know what those look like. And I also know that it only takes a subset of the rules of SQL to produce those queries. Because if I didn't write a single administrative related SQL statement, if I didn't include any deletes anywhere, why would I even need to interpret that? Why would I even need to interpret those statements at all? Can't I just say, oh, well, those are just not in my language. I'm not interested in those. And it turns out that, wow, what did I do? And it turns out that this works. Unfortunately, I didn't know a whole lot about development back then, and this project is sadly unmaintained. But as it turns out, other people had similar ideas. So in 2007, a guy by the name of Zed Shaw was doing a whole lot of Ruby on Rails development, and he was furious with the terrible state of Ruby performance on web servers. So he decided to screw it. I'm going to write my own. So he writes a web server named Mongrel, and instead of writing the HTTP parsing components in in Ruby or whatever, he decided to write it using the Regal state machine compiler. So Regal basically takes a description of a state machine, and it turns it into C. And he was able to turn around the first cut of Mongrel inside of a week by doing this. Now, I'm not talking about just the parser. He said the entire freaking web server inside of a week. And this is actually consistent with my experiences with trying to develop, say, like network software using parser generators. There's a library that TQ and I wrote last year, or started working on last year, that I'll be talking about in just a little bit, that's actually intended to make this kind of thing easier. And so once we had it working, we were like, all right, well, we need to write an example to show people what this is like. Let's do DNS. Well, I kind of ran out of time and ended up implementing DNS in the back seat of the car on the way from Leiden to Berlin, like the day before we had to give the talk. I spent about half the time on Reddit, and I got the thing done, so I guess about 3 hours of work all told for an entire DNS parser. Furthermore, they didn't just toss Mongrel and Apache against each other in some kind of shootout against, against cooked test data. No. They set up Apache, and then they set up Mongrel behind it, and then just let the internet go at it. And Mongrel just shut down 80% of the attacks that Apache just blindly let through. And this was in like 2008. And this turns out to be a huge performance win, because if there's no payload that you have to screw with, there's no CPU load that you have to deal with. So in 2010, Mongrel wasn't working out so well anymore for various reasons, and so Zed decided, all right, I'm going to throw it away, and I'm going to do Mongrel 2. It's going to be a language-agnostic platform, and I'm going to throw away everything except the parser, because the parser works. Zed was not the only person to have this idea. In 2008, Thin did the same thing. In 2009, Unicorn did it. In 2011, Puma. So, this actually leads me to an argument that I got into a couple of years ago with a guy from Google. I was telling him about the idea of full recognition before processing, and he was like, no, this couldn't possibly work. No, I mean, if Amazon were to do something like that, if Amazon were to throw away any malformed HTTP packet that came its way, they'd end up going out of business. So I said, all right, let's see who's actually using this kind of stuff. Twitter, as it turns out, when they were still a Rails app. Heroku. GitHub. Pretty much every Rails app you can imagine. It's a little surprising, actually, that like one of the worst languages on the web with respect to security actually has a parser that's doing better than just about everybody else out there. But I can't complain. I really can't. I wish everybody else would be doing this too. And I can't shit on Google too hard, because they did come up with protocol buffers. So what are protocol buffers good for? Well, protocol buffers are a way for sending messages from one place to another, right? Seems pretty simple. However, you don't pay attention to any of the actual details of the sending. All you have to do is say, this is what my data is. This is what it looks like. This is how it's laid out. And then you actually have a nice description that you can refer back to 6 months later down the line when you've forgotten everything about your design and you need to go and look what this field means. So Google themselves produced implementations in C++ and Java and Python. Other people have come up with other implementations. And so what this ends up meaning is that, if you've got two applications that, maybe they weren't, maybe the people that, maybe they have nothing to do with each other, but as long as they speak the same protocol buffer language defined within the confines of protocol buffers, they can talk to each other. All of the implementation details get abstracted away from you. You don't have to care about headers, you don't have to care about length fields, you don't have to care about anything other than what you specifically said in the definition you wanted to care about. You focus on the semantics, and the library takes care of the syntax for you. This is a theme that you're going to see coming up again and again and again. All right, moving on to 2013, a fellow by the name of James Coughlin, who also wrote a library called Fay, which is, if you're doing anything with pub/sub in Ruby or Node, you are probably using Fay. Fay is also built on top of Thin, so there's that mongrel HTTP parser again. But James is still going at it, and James is interested in language theory too, so let's talk about Websocket Driver. So this is what writing a WebSocket client implementation used to look like in, I'm not actually sure if that's Ruby or if I think that is Ruby. Okay, so you'll notice that there's this state field. What's that doing there? There's all this stuff where you have to keep track of leftovers. Why would I want to do a thing like that? This is way too much detail about the TCP and the HTTP parts of this than you want to have to care about as a developer. All you want to have to do is this. You want to say, I have a driver, and it takes care of all the WebSocket communication. And that's exactly what it does. It abstracts all the crap away from you. You do not have to keep the state in your head. There's this concept called processing fluency that I think is relevant to mention here. It's an idea from psychology. And it basically boils down to the less information, the less state about a thing you have to keep in your head while you're dealing with it, the easier it'll be for you to work with it. It's like when your processing fluency in your native language is very, very high because you're not having to keep track of a mental mapping of, oh God, what does this word mean and what order does the vocabulary go in? You just have that native fluency. And so what I'm hoping to see more of as this sort of development continues is reducing this sort of nonsense to this much smaller state to improve processing fluency and improve just developer capabilities across the board. Okay, and so moving on from HTTP, Flash. All right, so it turns out that Flash exploits, by and large, are not actually grammatically correct. The Flash interpreter will go ahead and run them anyway because lol Flash, but the file is itself malformed. What this means is that it's really, really simple to just write a recognizer that makes sure that the Flash file is actually correctly formed. And if it doesn't work, don't run it. This is perfect for protecting users. It also works with NoScript because NoScript has a plugin architecture. But beyond that, it's also useful for, say, for instance, ad networks. Because if I'm running an ad network and I want to know that I'm not serving up ads that are going to redirect people to phishing sites or whatever, I want to do some property validation. So I want to know, where is this ad forwarding to? I want to know if the widget that these people want to show my customers is going to load third-party content that's going to mess with them. And maybe I can't tell how much it, figuring out how much it messes with them would involve having to actually execute the code, but you can tell whether it loads third-party content. You know, that's a fairly simple semantic property. And with that, let's move on to the attack side of language-theoretic security. So that all got started in 2009 when Len Sassaman and Dan Kaminsky and I decided to start messing around with X509 and see what happened when we leveraged the differences between the X509 parsers like I described earlier. So the first attack that we noticed was also discovered by Moxie Marlinspike, who asked, what happens if you want to send off a CSR and you stick a null byte into it? You would, in most cases, end up getting back a cert with a null byte in the CN. So you know, you could ask for a cert for this subdomain with a null byte in it on evil.com, and you would get back that cert. But that doesn't mean that the browser saw it that way. Plenty of browsers just saw that null byte and they were like, oh, end of string, that's totally a valid cert for PayPal, rad. This isn't a problem anymore. That got fixed. But things were worse. Here are only two examples. So what happens when you decide to put more than one common name in a CSR? Turns out, some implementations will consider the first one canonical. Other ones will consider the last one canonical. You can actually put lots of them in there, and it was silly. It was not standardized. But if the certificate authority says, or if the certificate authority, say for instance, only cares about evil.com and goes ahead and signs it, and then sends that cert back to you, and you present that cert to a browser, and the browser just looks for and the browser looks at the first one, the cert is still signed. So that ended up being a certificate that looked completely legitimate for the common name that had not actually been validated. So here's another one. This is a representation of an object ID. So a similar representation that I didn't actually include on this slide resolves to 2.5.4.3, which is the OID for a common name. Well, this actually resolves to 2.5.4.2 to the 64th plus 3. Now in ASN1, which is the encoding that X509 is expressed in, that's supposed to be a big num. And in fact, OpenSSL does in fact treat that as a big num. So if I had put that OID with a string in a CSR and sent it to a CA running OpenSSL, then it would be like, I have no idea what the hell that OID is, so I'll just go ahead and sign this. And then I turn around and present it to Internet Explorer, which treated it as a 64-bit int, not as a big num. Overflow treats it as 2.5.4.3, and I suddenly have any cert I want. These are also fixed. There's a paper from Financial Cryptography 2010 that explains these and the other attacks that we did in substantially more detail, so I encourage you to check that one out because I do not have time to go through all of them. Okay, so after we did that, there was a veritable explosion of finding weird machines, by which we mean Turing machines embedded in the unlikeliest of places. So this all started in the debugger, when James Oakley and Sergey Bratus at PH Neutral, I believe, demonstrated arbitrary code execution in Dwarf. And then again in ELF metadata and the MMU trap handler. And then again in Mach-O metadata. And it's just going to keep going like this. When I gave the talk about the research that preceded this at CCC in 2011, I talked a little bit at the beginning about I talked a little bit about a talk that Cory Doctorow had given like the previous day, where he was talking about the coming war on general computation and how hostile governments and hostile corporations consider it in their interest to constrain the to constrain ordinary people's ability to compute things. I have to say, after the last 3 years of these guys finding weird machines pretty much everywhere they looked, the war on general computation is over. We won. But it just keeps going. So moving back to 2011, Travis Goodspeed riffed on, believe it or not, Orson Welles, the classic radio saga War of the Worlds, to come up with a file layer injection on the radio, starting in Zigbee and moving on. So what's packet and packet? It's basically an escaping problem. So in Zigbee, you've got packets with various fields in the header and then a body. And one of these fields in the header is called sync. There's a preamble, and then there's a sync, and then there's a body. What happens if you stick a sync in the body? Well, as it turns out, if there is, the hardware has no idea what to do about that, right? I mean, it's not the hardware's problem. It is fundamentally not the hardware's job to know anything whatsoever about layer 2. So if there's a symbol error that occurs while this radio is receiving, and it happens before the preamble and the sync or after the preamble and the sync, the receiver just goes, oh, well, that crapped out, I'll try again. And it just drops the rest of the packet and picks up at the next one. But if the preamble or the sync gets munged, which happens about 1 in every 1,000 packets, then the receiver thinks that the body is a brand new packet and picks up what it thinks is another layer 1 packet, but was actually embedded in the body. It turns out that encryption eliminates this problem, so Go WPA, like even WEP, is still good for something. And then, this is a little farther afield, but I want to bring this one into because this one's kind of near and dear to my heart. NetSob. So, a guy by the name of Marshall Beddoe back in 2005 raised the question, if we take like BLAST and Needleman-Wunsch and all of these great bioinformatics, local alignment and global alignment algorithms, what happens if we throw those at streams of data, streams of bytes, instead of streams of DNA code? He was mainly, at first he was mainly kind of wondering, well, can we just find out where the packets are? No, it turns out you can recover the whole damn grammar. And the NetSob guys picked this up and have been applying this to botnets. So they're running around owning botnet CNC protocols now, completely through information theory. Basically, the way this boils down is that Claude Shannon, the father of information theory, figured out back in the 20s or 30s that the information capacity of a channel dictates certain properties about like what you're able to transmit with it, and you end up being able to induce things from structure as long as you have enough patterns to work with. And so if you can watch a botnet and collect enough of its CNC traffic, then information theory can tell you what it's actually doing. So, moving on to the present day. There used to be this thing called C10K, 10,000 simultaneous connections. That's old and busted. The new hotness, 10 million simultaneous connections. So the argument being made here by Robert David Graham, who brought you things such as Black Ice, his assertion is that if you've got 8 cores and 64 gigs of RAM and a 10 gig Ethernet card, you ought to be able to handle 10 million simultaneous connections, no problem. Now, anybody who spent much time in the kernel is probably going, how the hell is that supposed to work? And the answer is don't. You do it all in user space. If you can watch his talk from ShmooCon this year to see all the crazy awesome stuff he did with PF Ring, it's insane, it's wonderful. At Black Hat, he'll be launching a DNS server that he wrote that parses the .com zone file faster than WC can do it. That's about 2 gigabits a second. And it would be faster, but there are cache misses when he's creating the zone table. So he'll probably have fixed that before Black Hat. I really recommend checking this one out if you can. All right, so now we actually get to talk about something I did. So last year, TQ and I decided that all this stuff with Beagle is really great, but unfortunately, it's an additional compilation step, and it's also just kind of something else to have to think about. Processing fluency again, right? If I'm writing in Python, I don't want to have to go shift headspace to a completely different language, especially if it's one that I only pull out when I have to write an input handler. Special purpose things like that are really easy to forget. So Hammer is inline domain-specific languages like you would find in Haskell or Scala, but for everybody. So we wrote it in C. You're not supposed to be able to do that because C is a strictly interpreted language, and when parser combinators were first invented, they were intended for, it's a thing that lazy languages make really, really easy, but it turns out you can do them with, you can do them in strictly evaluated languages with a few tricks, and we're just hiding all of that from you under the hood. So the API, as I said, is based on the parser combinators from Haskell and Scala. So what's a parser combinator anyway? Parser combinators are very small functions that do just one thing and one thing well, but you can compose them. So if I have the token parser, for instance, takes a string, and it will just parse that single token. There's another combinator that takes a range of characters and will parse one character in that range. The primitive ones, the primitive combinators just parse like concrete things, leaf nodes in trees, you might imagine. But for the non-leaf nodes, there are combinators that handle lists of things. There are combinators that handle like lists with separators. There are ones for recursion, and they're a really nice, expressive way to describe a grammar. And if you have bindings for them in your own language, which is what we're implementing, then you don't have to make that that state space shift in your head. Processing fluency remains high. Furthermore, Hammer also handles bitwise parsing, which absolutely no other parser combinator library, or really even parser generator library that I know of, does. I was sick and tired of saying, well, gee, I'd really like to deal with, I'd really like to write a Bison parser for TCP, but Bison only handles things byte by byte. I want to be able to handle things bit by bit, so we wrote one. And as I said, there is no separate compilation step. You can just plow that straight. You can just plow it straight into the code you're writing. And just like protocol buffers, the intent is for this to be write the protocol once and never, ever, ever have to implement it again. Furthermore, if one person's going to implement a protocol, why not let everybody have it? So we're doing a standard library as the follow-on project for Hammer. We'll be including a variety of message formats, file formats, codecs. The list is not really concretely in place yet. Things are still very much in the planning stages, but follow us on GitHub for news as it happens, particularly because we are planning on doing this as a bounty program. So the idea is going to be, you write an implementation that gets incorporated into the library, you get paid. That is the plan. If you are interested in sponsoring this, please feel free to see me after the talk. We've got a few lined up already, but it would never hurt to have more. So let's talk about IDRIS. This is going really way far afield. So I brought up Haskell a little bit earlier. So there's an even cooler thing than functional languages, and it's called dependent types. It's kind of like type system inception. Yo dog, I heard you like programming, so I put a programming language in your type system so you can program while you program. There are other languages that do this too, and one of Andreas' favorite languages, Coq, is an example of that. And I should have mentioned in these slides, but failed to, that Andreas has actually written a parser for PDF that is verified. He wrote it in Coq, so nobody make fun of the name. I'm sick of that. Agda. Agda's a weird one, and kind of nobody likes it because it's all Unicode all the time, and who has a Unicode keyboard anyway? But IDRIS, which was designed by a guy by the name of Edwin Brady out of the University of St. Andrews, is very close to Haskell, uses type annotations that are composable to describe to describe properties that the compiler then makes sure hold when when the code is actually running. So like all of your runtime checks, the compiler makes sure that there are no code paths generated that would violate a runtime check in the first place. And Edwin's goal for this is to make it really easy to prove security properties about implementations of protocols during the compilation stage. So Raichu asked, if we can have C on the web with Inscription, why not have dependent types on the web too? I mean, he was working at a Node shop, and I guess after you work with Node guys for a little while, you just get a little sick of the cowboy attitude, because that's what happened here. And so, long story short, he wrote a foreign function interface to IDRIS so that now the IDRIS compiler just compiles down to JavaScript on the back end, and so you can write your dependently typed web app that that has no possible code path, unless somebody manages to inject JavaScript into your session, and I guess you're screwed if that happens. But this is why compositionality matters. Point being, there are a lot of boundaries of competence out there. Between the browser and the network, between the browser and the operating system, between different layers of the browser, between different layers of the operating system, and it's like being the little Dutch boy in the dike, trying to stick our fingers in and plug all these holes. This is why reinventing the wheel all of the time with input handling is a problem. Everybody does the same. Everybody does what they think is the same thing, but they do it a little bit differently. And it's those little differences, like we discovered in X509, that lead to major vulnerabilities later on down the line. So it may sound like, it may sound a little silly to worry about dependently typed JavaScript now, but that's okay. This is ahead of the game. This showed up early. I was not planning on this to be here this soon, but it's ready and it's waiting for us. So, it's been a long, strange 8 years. And I talked a lot faster than I thought I was going to. That's kind of funny too. So I haven't talked a lot about what's coming in the next, in the next 3 to 5 years, as I kind of hinted at. But for that, I actually kind of want to defer to a Dutch member of the European Parliament, Meredith L, who last week wrote a very compelling essay about cyber war. And in it, she pointed out that in global politics these days, we're being asked to believe that a state of perpetual war is something that we should just accept. That the Cold War is coming back again, and this time it's all going to be fought online. And it just isn't true. I mean, what we've learned, the most important thing we've learned in the last 8 years is that we can build things better. We can build things more robustly. We can build things that run faster because they are stronger. And so, in response to Monique's invitation, all I can say is, bring it, we're ready. Let's do this. Any questions?
now it works. So are there any questions? I believe there's no question at all.
All right, thank you very much for your time.